So, good afternoon, everyone. Today is the 11th class of the Chemical Process Technology live sessions. In this week, Sir has talked about the terephthalic acid production, the DMT production, and from that PET production, and about the biorefineries. He talks about the biorefineries. We will discuss that we'll start the lecture in 5 minutes. So, let's start the session. So, let's start the session. So, our first question is DMT produces PET by polycondensation with ethyl alcohol. DMT produces PET by polycondensation with ethyl alcohol. Is it true or false? So the answer is false. Answer is false because DMT is dimethyl terephthalate and PET is PET is polythene terephthalate. Polythene terephthalate, right? So this is the polymer and its monomer is DMT. So DMT from DMT, PET is definitely produced by, it is not the polycondensation with ethyl alcohol. It is polycondensation with ethylene glycol. So polycondensation with ethylene glycol. Okay, so that is why it is false. Next question. Which material can eliminate the methanol recovery phase in PET production? Which material can eliminate the methanol recovery phase in PET production? Which material can be used for elimination of methanol recovery phase? The answer is TPA, that is the terephthalic acid. So it is also one of the monomer of PET. Okay, so TPA can eliminate the methanol recovery phase in PET production. TPA has the advantage in the production of PET compared to DMT. Is it true or false? TPA has the advantage in the production of PET compared to DMT. Is it true or false? The answer is true because when you use TPA as the monomer, it will increase the production of PET per kilogram. Okay, so that is why TPA is used. So the advantage reason is so TPA increases the yield per kilogram of starting material. Okay, so there is a there is a connection loss. Sorry. Again I'm starting. So the TPA has the advantage over DMT because TPA increases the yield per kg of starting material, and it can eliminate the methanol recovery phase, which will obviously decrease the whole cost of the industry, right? So that is why TPA is used for production of TPA has an advantage in the production of PET compared to DMT. That is true. Next question. Why is ester not favored over acid? Why is ester not favored over acid? So, for any kind of polymer production, monomer has to be pure. Okay, that means in case of this PET production, monomers are DMT and TPA, so DMT or TPA has to be pure. Okay. Pure for the production of PET, right? And DMT is much more pure than TPA. Okay. So monomers or synthesis polyester are some of the purest and most abundant compounds. So DMT is the ester. So here DMT is the ester and TPA is the acid. Okay. So DMT is obviously pure. But what happens? However, DMT is difficult to purify as it is non-volatile, insoluble in common solvents like acetic acid or ethanol, any kinds of solvents, and does not melt. Okay. So for these reasons, DMT, that is the ester separation is or ester purification is very much difficult. But acid does not have any kind of these problems. Okay, acid is that is the terephthalic acid is easily separable or easily it can be easily purified, and also it can give much amount of production, right, per kg. So that is why. So you can write here that acid is easier to purify and also it can yield more amount of PET. So that is why acid is preferred over ester, even if the ester is much more pure than the acid. Okay, so this is the reason you can, if you write in your own language, this is the example I am showing. Okay, next. What is the raw material used in the production of monomer of PET? What is the raw material used in the production of monomer of PET? So the monomer is not para-toluene but para-xylene. Okay, not orthoxylene either. Okay, so para-xylene is this. This is para-xylene. What is orthoxylene? Orthoxylene is this. Okay, this is orthoxylene and this is metaxylene. Hmm. So this is the different types of xylene, but in case of polyethylene terephthalate production, we use para-xylene. Okay, p-xylene. Next, why is oxidation process not used in TPA production? Why is oxidation process not used in terephthalic acid production? The question is, why is oxidation process not used in terephthalic acid production? So, so we know that terephthalic acid is obtained from terephthalic is obtained from p-xylene. So we oxidize p-xylene to get TPA. So it is not like that TPA, we cannot get TPA from the oxidation of terephthalic acid, right? So obviously that is the p-xylene after oxidation produces terephthalic acid. But this is the final step. Okay, this is the overall reaction. But in the first step, what happens? In the first step, what happens? So in the first step, P paraxylene reacts with oxygen or 3 by 2 of I think, whatever, reacts with oxygen and produces so this is P toluic acid. Okay, so in this the overall process, this is the overall process. The first step is to produce the toluic acid. What is the problem here? So if we further oxidize P toluic acid, the process is extremely slow due to the strong stability of para-toluic acid. So we don't directly oxidize it. We do oxidize it, but not only the oxygen is given in this process. So if we use nitric acid, then this para-toluic acid step will be gone and directly TPA will be formed. Okay, because nitric acid is very potent oxidant, so then it paraxylene can do the oxidation step to produce the TPA. Okay, so this is the process. So TPA is not TPA is not used in the oxidation process because it produces first it produces para-toluic acid, which is extremely stable, and that doesn't go further. Then the process is very slow, and almost it won't convert into TPA anymore. So we have to use another way, that is the nitric. We can use either nitric acid, or we have to use some other kinds of like to increase the speed of the process. Okay, that is why this is not directly oxidized. The paraxylene is not directly oxidized to produce TPA, that is the terephthalic acid. Next question is, explain the TPA production reaction. Explain the TPA production reaction. So this is the process we have just learned, that paraxylene with nitric acid can produce terephthalic acid, 4 moles of water and 4 moles of nitrous oxide. This is TPA, right? So this is the process. This is an exothermic process. Next, what is the catalyst used for the oxidation of p-xylene? What is the catalyst used in the oxidation of p-xylene? The answer is cobalt based catalyst. The answer is cobalt-based catalyst. The name of the catalysts are cobalt acetate or cobalt naphthenate. Okay. So this is a cobalt-based catalyst used for the oxidation of the p-xylene. Esterification of p-xylene needs catalysts. Esterification of the p-xylene needs catalysts. Is it true or false? Is it true or false? It is false. So oxidation process needs catalyst. P-xylene oxidation process needs catalyst, not the esterification process. Okay, so it is false. Discuss the Wheaton process. Discuss the Wheaton process. So in this process, so in Wheaton process, P-xylene undergoes four alternative oxidation and esterification reactions. Okay, so first we'll study that. First there is only the P-xylene. This is paraxylene. It will be oxidized with 1.5 of oxygen moles. So what will happen? Dehydrogenation will happen and it will produce this is the para-toluic acid. Next, so first is the oxidation step. Next is the esterification step. Here we'll add methanol. So here oxygen is added and water is gone. Here methanol is added and again the water is gone. That is the dehydrogenation only happen. So what will happen? It will produce para methyl toluate. Okay. Next again the oxidation step will happen. That means oxygen will be added and water is going out. Here also now it will top it will be COOCH3 and the bottom from bottom water will be taken out. It will change to okay, so its name is methyl terephthalate. And from here again we will add the methanol, that is the esterification reaction, and water will be taken out and it will produce this is the dimethyl terephthalate, that is DMT. Okay, so in the Wheaton process, we oxidize. So first we have oxidized here, produced p-toluic acid, then we did the acidification, produced p-methyl toluate, then again oxidation, it produces methyl terephthalate, then again acidification, it produces dimethyl terephthalate. So from Wheaton process, we do the oxidation and acidification reaction of p-xylene and produces DMT, which is one of the monomers of PET, right? So this is the whole process. Next, Amoco process needs bromine atoms. Amoco process needs bromine atoms. Is it true or false? So Amoco process needs bromine atoms. It is true. So bromine atoms is reactive radicals. Reactive radicals, bromine atoms, which is available in the form of NaBr, sodium bromide. Okay. Next question. Which technique creates polymer grade TPA by the oxidation of p-xylene? Which technique creates polymer grade TPA by the oxidation of p-xylene? So the answer is Amoco process produces polymer grade TPA, okay, by the oxidation of paraxylene. Next question, what is the physical condition maintained in oxidation reactor in the Wheaton process? What is the physical condition needs to be maintained in the oxidation reactor in the Wheaton process? The answer is 430 Kelvin and 6 bar, right? And what is the physical condition maintained in the esterification reactor in the Wheaton process? So in the Wheaton process, we have seen there are two types of reactions happening continuously. That is the oxidation reaction and esterification reaction are happening alternatively, right? So in this case, the temperature is 430 Kelvin and 6 bar. And in this case, the temperature is 520 Kelvin and 25 bar. Okay. Which chemical method is used to purify crude DMT? Which chemical method is used to purify crude DMT? The answer is crystallization. Okay. So with the help of crystallization, we purify crude DMT. But as I said, DMT purification is uh, costlier than the TPA. Next question, what catalysts are used in the oxidation reaction in Witten and Amoco process? So, in the Witten process, in the oxidation reaction, catalyst is used cobalt naphthalate. Hmm. Naphthalate actually, sorry. So, this is cobalt naphthalate. Okay. And in the Amoco process, it is used, the catalyst is used cobalt acetate with Br, that means with bromine or enhanced by bromine. Enhanced by bromine. So that is how so that is the difference in the catalyst used for the oxidation process into different methods. Next question. Acetic acid is one of the reactants in Witten process. Is it true or false? Acetic acid is one of the reactants in Witten process. Is it true or false? So the answer is false because acetic acid is used in Witten Amoco process. And in the solvent of Amoco process, you have seen the solvent is cobalt acetate enhanced by bromine, right? So this acetic acid is used as the catalyst solvent. Okay. So that is why acetic acid needs to be present in the Amoco process but not in the Witten process. Next question. High pressure is maintained at the oxidation reactor in Amoco process. Is it true or false? High pressure is maintained at the oxidation reactor in Amoco process. The answer is true, because in the Witten process, the pressure is 6 bar and temperature is 430 Kelvin. And in the Amoco process, the pressure is 25 bar and temperature is 470 Kelvin. So high pressure is maintained at the oxidation reactor. Next, why is TPA got crystallized in Amoco process? Why is TPA got crystallized in Amoco process? So, in the Amoco process, what happens? In the oxidation reaction itself, the paraxylene converts to acetic acid, because only this is a single step process. In the oxidation reaction, paraxylene produces. So, in the oxidation reactor, paraxylene produces TPA using acetic acid solvent for cobalt acetate and sodium bromide based catalysts. So acetic acid is present in the reactant, right? So this TPA is less soluble in acetic acid. Okay, so its amount is 0.13 gram per kg at ambient temperature and 15 gram per kg at 470 Kelvin. So that is the reason, that is as TPA is slightly soluble or less soluble in acetic acid, that is why TPA crystallizes during its formation. Next question. What is the contaminant for TPA and how to remove it? So the contaminant is 4-formyl benzoic acid, that is also known as or 4-carboxy benzaldehyde. Okay, this is called 4-CBA. So this is the contaminant which co-crystallizes with TPA and is an intermediary in the oxidation process. And while the production of polyethylene terephthalate from terephthalic acid, this 4-CBA terminates the esterification chain, and that is why it is necessary to purify at that step. And also 4-CBA discolors the polymers, and that is why it needs to be eliminated from the TPA, right? So what is the methods for removing it? So there are two methods. One is the quartz TPA is mixed with water and heated until it completely dissolves. A palladium catalyst is used to convert 4-CBA to p-toluic acid. Okay. Quartz TPA is mixed first. Quartz TPA is mixed with the water and heated until it completely dissolves. Then a palladium catalyst is used to convert the 4-CBA to p-toluic acid. This is the second step. And why is it converted in p-toluic acid? Because the solubility of p-toluic acid is greater than that of 4-CBA, that is the contaminant, and it does not co-crystallizes with TPA. Okay, so once the the TPA as well as the contaminant, both of them become crystallites in the oxidation reactor itself. So quartz TPA is mixed with water and heated until it completely dissolves, and then palladium catalyst is used to convert this contaminant to p-toluic acid. Now the solubility of p-toluic acid is greater than that of the 4-CBA or the contaminant, and it does not co-crystallize with TPA. So that is how we can separate the TPA from the p-toluic acid as well as the contaminant, right? So this is the reason. Next question, Amoco process is corrosive due to the presence of what? Amoco process is corrosive due to the presence of bromine, that is the sodium bromide form, and the acetic acid, not for the catalyst or not for the ethyl alcohol. Ethyl alcohol has no contribution in the reaction at all. So it is only because of the bromine and acetic acid. Amoco process is corrosive. That is why to reduce the corrosion, we use Hastelloy C or titanium for the reactor material. Next question is, which process is used for the production of TPA? Is it true or false? So you know that in the Whittain process, we have seen that after oxidation and alternative oxidation and esterification of p-xylene leads to the formation of DMT, that is dimethyl terephthalate. So Whittain process is not used for the production of TPA. So it is false. So Amoco process is used. So in the Amoco process, TPA is produced by oxidation of p-xylene. How? Because I have earlier said that if we oxidize p-xylene, it will produce p-toluic acid, and further it will not oxidize, or it will oxidize at a very slow rate, which will not reach to the point of the formation of terephthalic acid. But what in the Amoco process, what is the difference we do? Here we include extremely reactive materials such as bromine atoms in the form of sodium bromide with acetic acid and oxygen. Okay, so oxygen needs to be solved for the oxidation process of p-xylene. So along with oxygen, acetic acid and sodium bromide is also as a radical also supplied to the reactor, and when the first p-toluic acid is formed, these radicals of bromine attack the p-toluic acid, and once the p-toluic acid radical is, and that will lead to the production of p-toluic acid radical. So now once the p-toluic acid radical is produced, the reaction can proceed similarly to the oxidation of p-xylene and leading to the synthesis of TPA. So that means bromine radicals of bromine attack the p-toluic acid, and that is how p-toluic acid removed from the steam, and now the original oxidation happens, and that of original oxidation of the p-xylene happens, and that will lead to the formation of terephthalic acid, and the reaction is the similar one, only the p-xylene the oxygen, and it produces TPA plus water. So in the middle process, as an intermediate product where p-toluic acid is produced, it is removed by the radicals of bromine, and that is why we use the radicals of bromine and acetic acid as a solvent. This is the difference. So Amoco process is used for the production of TPA. Okay. Next, what is biorefinery? What is biorefinery? So I'll show you a video of biorefinery. So let's copy the link. Let's copy the link and
When you write, your tone influences how readers respond. With Grammarly, just highlight your text and type how you want to sound.
Have you ever heard about biorefineries?
I hope the screen is visible.
Before delving into biorefineries, it's crucial to understand what biomass is.
So maybe the record, you cannot see the, you can listen to the sounds of the video. So I am here, it is doing. I have on the subtitles, you can read and understand the biomass. So it is very easy.
United Nations Framework Convention on Climate Change describes biomass as non-fossilized, biodegradable organic matter derived from plants, animals, and microorganisms.
So it is the biomass is derived from the plant, animals, and microorganisms. Okay.
In simpler terms, it's any biologically sourced, non-fossil raw material.
So you can see that here the raw material is biologically sourced or non-fossil. Okay, it is not like gasoline or this carbon or this kind of things. It is biologically sourced.
Now, armed with the definition of biomass, we can also define what a biorefinery is. According to the National Renewable Energy Laboratory in the United States, a biorefinery is a unit that integrates equipment and processes for converting biomass into chemicals, fuels, energy, or marketable materials.
So in the industry, these biologically sourced materials are converted into different type of chemicals, fuels, energy, or marketables.
Traditional industrial plants for paper and pulp, ethanol, and soybean oil are well-known examples of biorefineries. Biorefineries can be classified by the type of processed biomass. First-generation ones use conventional agricultural raw materials or their primary products like grains, sugars, and vegetable oils, and have mature and well-established.
So there are 3 to 4 type of generation of biofuels or biorefineries. So this is the first generation biofuels about biorefineries where sugars, conventional agricultural products such as sugars, vegetable oils are used as the raw material.
Established technologies. Second-generation biorefineries convert agro-industrial and forestry waste as well as non-food crop sources into.
So in the second generation, we use agro-industrial, forestry waste and non-food crops. Okay.
Bioproducts and advanced biofuels. In third-generation biorefineries, oils, biofuels, foods, and pharmaceutical products can be obtained from algae.
So in the third generation, we use the foods extract, the pharmaceutical extract, and the fuel extract. Okay.
Second and later generation biorefinery technologies require a higher level of sophistication and are in the early stages of development. As plants and some algae capture CO2 from the atmosphere to produce their food, biomass has the potential to be a practically carbon-neutral source.
So in the last generation, which is in the development phase, where the algae are used as the source of biomass for the fourth generation biorefinery, where they don't use the CO2, so it will reduce the CO2 consumption also.
Its use as a raw material represents a significant bet on transitioning to a renewable carbon-based economy, also known as the bioeconomy. A recent study from the University of Athens, published in January 2024, provides a review of circular economy practices in the agricultural sector. The article emphasizes the importance of maximizing biomass usage, valuing its byproducts and waste to reduce environmental impact.
So it is a study about the bioeconomy, where they have shown the biomass used for the biorefinery is how much economically profitable, or it won't have any bad effect on the environment also.
Thus, second-generation and later biorefineries play a crucial role in the circular economy. At this point, you might be thinking that if biorefineries use renewable carbon sources and contribute to the circular economy, they are a solution to the climate crisis. Right? Well, it's true that many academic studies suggest better environmental performance from biorefineries compared to fossil processes, especially in advanced generations. But it's not always the case. A 2021 study from the University of Ferrara, Italy, compared the life cycle assessment of water bottles made from virgin petrochemical PET and PLA, a biopolymer obtained from first-generation sugar fermentation. PET bottles outperformed in 9 out of 11 impact categories, emitting 0.134 kilograms of CO2 equivalent per PET bottle compared to 0.616 kilograms of CO2 equivalent per PLA bottle. This occurs because, despite biomass's carbon capture, there are emissions associated with its cultivation and transformation. During cultivation, emissions from fertilizer, pesticide use, and fossil fuels in planting and harvesting machines, as well as transportation from the field to the processing unit, contribute to increasing a biorefinery's carbon footprint. In production, process technologies are often more advanced, demanding higher specific energy consumption than petrochemical plants. Therefore, when the energy used is fossil,
So here they are saying that even if we are using biomass, still the carbon footprint is high for the biorefineries also. So how to
based,
remove
like
that?
coal or natural gas, carbon emissions also increase. Beyond environmental aspects, other obstacles hinder replacing petroleum, natural gas, and coal-derived products with bioproducts. A technical barrier involves raw material collection and storage. Usually, significantly more biomass is needed to produce the same amount of a bioproduct equivalent to a fossil-based one.
So here is one of the disadvantage of biorefinery because
The higher demand for
because
feedstock
because here the more amounts of biomass is needed for producing of the same amount of fuel, right? So that is why it is a disadvantage of.
of a bioproduct equivalent to a fossil-based one. The higher demand for feedstock implies a logistical challenge. Collecting more from larger areas and storing in large quantities. Biomass storage is also complex as it easily degrades. Another
These are the disadvantages of the biorefineries.
technical challenge lies in conversion processes.
So
First
the conversion process is also the transportation process, storage process, conversion process are the disadvantages for the biomass.
generation biorefineries have mature process technologies, methods for algae and waste-based biorefineries are in early development. Although there are validated technologies in labs and demonstration plants, scaling these processes to industrial units is an obstacle.
Another one is the conversion process. So we can do the biorefinery in the lab scale level, but to imply it in an industrial plant is difficult.
Bioproducts are often obtained in diluted solutions, posing challenges due to intensive energy use for product concentration. Moreover, dilution and typically long residence times result in the need for large equipment with high specific volumes, especially compared to conventional fossil plants. Despite these technical issues being barriers to new biorefinery construction, the major challenge is economic. The transportation cost related
So this is the economic disadvantages for the biorefineries.
to collecting a larger biomass volume in vast cultivation areas and long distances to the plant often makes feedstock more expensive.
So it makes feedstock more expensive because the transportation is difficult from one place to another place.
The high energy consumption of purification steps also contributes to increased operational costs. Additionally, large equipment volumes and the need for more separation steps considerably raise capital expenditure in a biorefinery. In summary, by utilizing biomass and waste for bioproduct and biofuel production, biorefineries stand out in seeking sustainable solutions for the climate crisis and have great potential to contribute to transitioning to a low-carbon, fossil-free matrix and a circular economy model. However, the environmental footprint of bioproducts is not always smaller, requiring meticulous analysis using tools like life cycle assessment for correct environmental impact calculations. Ultimately, for biorefineries to become viable, investment in research for developing more efficient technologies and reducing production costs is necessary. This video was produced by Marilia Kavanaghi and Renato Araújo.
So we are acknowledging here the Marula Kavanaghi for this video, and we have learned from here that although this biomass production with the help of the bioresourced solution, that is agricultural waste, then the forestry waste, then the algae, these are very helpful for sustainable bio solutions. It will reduce the carbon footprints, but on the other hand, it has some challenges because of the transportation cost will increase, the conversion rate is low, and the amount of raw material needed is much more higher than compared to the fossil fuel to produce a minimum amount of biofuel, right? So that is why these are the challenges we need to take care of. Next question. At 1 ton of dried biomass gives liter of cellulosic alcohol. So biorefineries are important for energy, fuel, materials, and chemical demand is growing up. Then we know that there is limited amount of fossil fuel left, and if we use the bioresourced materials, raw materials, then it will reduce the carbon footprint that will lead to the reduction in the climate change or greenhouse gas effect, and that will increase the global economy also. But still, there are some challenges. So, coming to this question, 1 ton of dried biomass gives 250 liters of cellulosic alcohol. 1 ton of dried biomass gives 250 liters of cellulosic alcohol. Next question. From which biomass ethanol production is the highest? So, this is not the wheat straw, but this is the rice straw. So, from all of them, the ethanol can be produced, but the ethanol production rate is higher in case of rice straw, if we use the rice straw as a raw material. So, we'll know so for wheat straw, the value is 28 billion liter per year. For rice straw, it is 42.5. For cotton stalk, it is 13.2. And for sugarcane bagasse, it is just 3. Okay, so that is how we can see that rice straw is the highest. Next, discuss the categories of biofuel. So, the first one is the first generation or 1G biofuels. So first one is the first generation or 1G biofuels, right? So we will also call it 1G, and its raw materials are cereals, sugarcane, bagasse, right? Okay. So these are the basic biofuels. So first generation is the basic biofuel. Second one is the second generation, that is 2G, and its use non-edible plant agricultural and municipal waste. And the third one is the third generation, that is 3G, and it uses microalgae microbes as the raw material. So these 2 and 3 are the advanced biofuels. These 2 and 3 are advanced biofuels. Next, no separate environmental clearance is required to produce 2G ethanol. Is it true or false? No separate environmental clearance is required to produce 2G ethanol. And it is true. Next question, what are the products of the biomass processing technology? What are the products of the biomass processing technology? So using biomass processing technology, what products we can produce? So first one is the fuel grade bioethanol. So this can be used as a fuel in the cars and many things, cars, trucks, and this kind of transportation. Second one is the biochemicals. Example like HMF, furfural. Okay. The third one is the bio-CNG. So bio-compressed natural gases we can use, which can be used in the small autos where you used now the CNG. Four is the liquid CO2. Fifth one, power, like steam. So if we use steam as power in every industry, the cost will be much more reduced, and the uh, steam can be reused in the production industry itself, so it will not be wasted, right? And the last one is the biofertilizer. So these are the products of the biomass processing technology. Next question, discuss the classification of biorefineries. So just I have told that there are biofuels also and biorefinery. So 1G biorefinery. For this case, the raw material is edible, includes simple sugar, okay, then cereal starch, then vegetable oils, then animal fats. These are the basic biorefineries. Second one is the 2G biorefinery. And these are the non-edible raw materials. Includes agro waste, that means agricultural wastes, forestry waste, that is the forestry waste. Then comes energy crops, then comes the municipal solid waste. That means the solid waste come from the home. Okay. Then there are the third generation biorefinery. So the 3G biorefinery includes biomass of fresh water algae, then marine algae, etc. Okay. And the last one is the 4G biorefinery, which includes vegetable oil and genetically modified microorganisms, that is GMO. Okay, so these are the 4 classes of biorefinery. Next question, what are the advantages and disadvantages of 1G biorefinery? So we have seen that in the first generation biorefinery, the edible oil like rapeseed, edible things are the raw materials like rapeseed oil, sugar cane, corn starch, right? And it will produces biodiesel, bioethanol, polylactic acid, right? So, but there are some disadvantages and advantages also. So advantages are obviously that 60% up to 60% reduction of greenhouse gas emission compared to fossil fuel. And the second one is the easy hydrolyzable biomasses. But the disadvantages are intensive use of lands. So for the search of biomass, for the search of sugar cane, rice straw and those stuff, we need to intensively use the lands, right? And competition with food and feed production. Okay, so that will lead to the competition between food and the feed production. So if these are edible part, right? So if we use this as a feed for the refineries, then what will we use for the food also, right? So there is a competition between there is a contradiction between the food and feed production, and continuously the competition is happening, and that is the disadvantages of 1G biorefineries because it uses edible part of the food as raw materials. Next question. 3G biorefinery is referred as the forest biorefinery. Is it true or false? So it is false because 2G biorefinery is referred as forest biorefinery. Next question. Lignocellulosic based refineries come under 2G biorefinery. So we have just said that 2G biorefinery is referred as a forest biorefinery. So all the materials or the non-edible part can come under the 2G biorefinery, and under them obviously the lignocellulosic based biorefineries are there. That means in the forest we could get the wood and the leaves of the tree, right? So these are all the lignocellulosic based biorefineries. So under the lignocellulosic based biorefinery, under this comes cellulose, which is available in the wood, then hemicellulose, which is important part of a tree, then lignin, then direct extractables. So the answer is true. Next, which biorefinery provides sustainable circular bioeconomy? The answer is 3G. So 3G biorefineries provide sustainable circular bioeconomy. Next, discuss the 3G and 4G biorefineries in details. So I am not writing here, I am just showing you the slides. It will be better from study directly from there. Okay, so yes, so this is the, as it has asked to discuss in details. So I am showing you, this is the third generation biorefineries. You have seen that it is the advanced biorefineries where sustainable circular bioeconomy is provided, and all the type of algae are the raw materials like macro and micro algae, phytoplankton based biorefineries. Okay, so these algae are available in any kind of water bodies, right? So from there is, under this it comes the cellulose, red, green, brown algae. So from red, green, brown algae we can collect cellulose. From green algae we can collect starch. From brown algae and seaweeds we can collect alginate, which can be transferred to alginic acid. Then freshwater lake, agar, red algae, and seaweeds, mannitol is opted. Okay, so these are the raw materials for 3G biorefinery. But it still has some pros and cons. So no competition for the arable land, cost effective and environmentally sustainable. As you can see, it is sustainable and provides appreciable valuable compounds. But cons are what? Higher greenhouse gas emission than 2G and large scale feasibility. So it can be done in one water body or two water bodies, but to include all the water bodies in the world, it is difficult to feasible. It is difficult. So that is why the feasible problem comes. Otherwise, the method is very helpful to the environmentally sustainable also, but it is not largely scalable, and also the higher greenhouse gas emission than the 2G. So this is the 3G biorefinery. When this type of question is asked, you have to give the details like the raw materials, the pros and the cons, the way it has written here. Okay. Next comes the 4G biorefinery. The 4G biorefinery is based on raw materials that are inexhaustible, cheap and widely available. right? So some wastes are not exhaustible. So that is why these 4G biorefineries come. So widely used feedstock is biomass from the municipal vegetable well oils. So the waste we produce in the municipal, in the school in premises or in the office premises. So these kind of solid waste are used as the feedstock for the 4G biorefinery. So reduces the recurring issue of treatment and management of these wastes. And the processes are mostly thermochemical and most of them are used in industrial scale. So MSW, if I see the flow chart, if we give the temperature, it will lead to incomplete combustion and that will lead to dioxin or furans production. Okay. Pros is improved photosynthetic efficiency and biomass accumulation, but the con is early stage of development. So it needs early stage development because if we heat the MSW, that will lead to another pollution, right? Another air pollution. So we have to manage there how to use that. So these are the examples of or explanation for the 3G and 4G biorefineries. Next, gasification comes under which conversion in biorefinery? So gasification comes under thermal conversion of biorefinery. Okay. Next, what are the four conversions of biorefinery? So one is the thermal I have just shown you. So the first one is the thermal conversion. So where this gasification, pyrolysis and so let me write the four first. Then comes the biological conversion, then comes the chemical conversion, and then comes the mechanical conversion. So if you see the chart here, excuse me, you see the chart here. So these are the four types of conversion in biorefinery. So in the thermal conversion or thermochemical conversion also you can say. So in the thermochemical conversion, you can see that first the gasification happens. Gasification or pyrolysis or combustion of the raw material happens. It will produce pyrolysis oil, product, gas, steam or heat, and it will finally lead to the production of biofuel, biochemicals, syngas or olefins or electricity. From there it can be used in electricity. In the biological conversion, you can see the anaerobic digestion of the raw materials happens in enzymatic hydrolysis, fermentation. It will lead to the production of biogas, fermentable sugars, and ethanol. Then finally, biomethane, bioethanol, and methanol can be produced. In the chemical conversion, the methods are acid hydrolysis, supercritical conversion, solvent extraction. It will produce cellulose, hemicellulose, lignin, and finally, from there we can produce biofuel, bioethanol, fermentable sugars. Last one is the mechanical conversion. Here the methods used are drying, extraction, separation. Here also lignin can be produced as well as vegetable oils, biofuels are also produced, and it will lead to biomaterials, biochemicals and electricity as well. So this is the thermochemical. Okay, so gasification comes under the thermochemical conversion. So here is also it is not only thermal, it is rather thermochemical conversion. That means here temperature is also given and chemical conversion is also happening. Next, discuss the types of biorefinery infrastructure. So the first infrastructure is the brownfield refinery. Second one is the greenfield biorefinery. And the third one is the retrofit biorefinery. Okay, so if in exam this type of question asks, you have to write the whole thing. I am writing the main point and showing the details or points from the slide, but in the exam you have to write point wise. And the what is the work right here, the brownfield biorefinery, here it is space occupied from previous user, limited space, difficulty in future development, easy accommodation for crew members, easy access to local suppliers, demolition requirement can increase project cost, no governmental restrictions, local interfering can delay projects, brownfield development localizes communities in a limited congested region. So this is the one type of infrastructure in brownfield biorefinery. Next is the greenfield biorefinery. Here, space can be used from scratch, ample space, future expansion possible. Accommodation could be difficult, so must be built beforehand. Limited local suppliers in undeveloped locations. Then completely new, so no demolition. There could be governmental restrictions if deforestation or similar environmental issue arises. No chances of local interference, reduced traffic and congestion. So in the brownfield there is congestion, but in greenfield there is not. And retrofit biorefinery is integration of new technology within existing structure, can improve energy efficiency, can be helpful in diversifying the product portfolio, helpful in reducing emissions, advantageous in usage of existing supply chain, reduction in capital costs. So these are the three types of infrastructures. Any of them can be used as per the requirement. Next question, what are the byproducts of biorefinery? So, byproducts are, first one is the lignin-rich kick, which is separated from the solid liquid separation and used as a boiler fuel along with supplementary fuel. Then comes raw carbon dioxide gas. It is generated during fermentation and vented off to atmosphere after scrubbing with water. Third one is the technical alcohol. This is solid in the market for production of chemicals or can be blended with fuel ethanol. Okay. Fourth one is the fused oils. A mixture of higher alcohols removed from the system is burnt in boiler. Fifth byproduct is sludge from process condensate treatment plant. It may be used as manure for agricultural field. And the sixth one is the ash. Ash is generated in boiler, may be sold to bricks and cement industry. So these are the 6 byproducts in biorefinery. Next, what is the use of impure spirit? So we have just seen that in technical alcohol is nothing but impure spirit, and it is sold in the market for production of chemicals. Production of chemicals or can be blended with fuel ethanol. Next, what is biobutanol? What is biobutanol? Biobutanol is an alternative energy source due to its properties. So, like it is also an biofuel, right? Like bioethanol, it is biobutanol. So, but it has higher calorific value than ethanol. You have to write all the properties. Then easily mixed with gasoline in any proportion. Third advantage is lower flammability. And hydrophilicity. And how biobutanol is produced? It is after ABE, that is acetone, butanol, ethanol fermentation. Biobutanol is produced, and it is produced here. The bacteria is used is Clostridium acetobutylicum. There is a bacteria used for this fermentation, and ABE is mixed at this ratio 3:6:1. Okay, so maximum. So you have to tell that in butanol is used for from acetone butanol ethanol fermentation with the help of Clostridium bacteria, and it is mixed in the proportion of 3:6:1, and maximum concentration in this mixture, like in this ratio, if we mix the raw materials or reactants, then maximum concentration of butanol is 10 gram per liter. Okay, so this is how biobutanol is produced, and these are the some of the important properties of the biobutanol. Next question: what is the effective technique to separate butanol in ABE process? What is the effective technique to separate butanol in ABE process? So the answer is distillation. So distillation is the most effective. Others are also there, obviously. Stripping is also there, absorption is also there, pervaporation is also there. The first one is the so in this four, the first most effective is the distillation. Then comes the stripping. Then comes the pervaporation. And then comes the absorption. Okay. Next question. What are the chemicals used in first model of car? What are the chemicals used in first model of car? The answer is gasoline, ethanol, or a blend of them. In the first model of car, gasoline, ethanol, and or a blend of them was used. Next question. What is biofuel? So here also I have a video So
And we're back in third quarter planning. Adams is quarterbacking this project, and she is.
so you also here see the
Can you name some fuels that can be burned to generate energy? Coal, oil.
here also you can see the making of biofuels, how biofuels are made. Okay, I have switched on the this captions block. We are able to see it. So
and gas are probably the first that come to mind. In this video, we're going to look at another special type, biofuels. We have fossil fuels to thank for providing us with energy that has been used for many huge advances in society. However, they also have some serious disadvantages. Burning fossil fuels releases carbon dioxide, which is a major contributor to global warming. Sulfur dioxide gas is also released, which makes acid rain, damaging the habitats of organisms. And oxides of nitrogen are produced, which can cause lots of breathing problems, especially for people who suffer with asthma. With our growing global population of 7.5 billion, we have ever-increasing energy demands. We need more environmentally friendly, cleaner, renewable alternatives.
so if we use fossil fuel, we know already that they can produce CO2, which will the greenhouse effect. Then there is SO2, sulfur dioxide or sulfuric acid. It will produce acid rain. Then there is nitric acid contamination is there. So these are the disadvantages of the use of using fossil fuel. But our demand is increasing day by day, right? So how we'll manage that demand, because fossil fuels are also limited in this earth, right? So how we'll manage our society, how we'll manage our environment and keep it sustainable, and also meet our demand, because there are 7.5 billion people currently living in this world.
So what are biofuels? Biofuels are produced from living matter. They have many advantages, but some disadvantages over burning fossil fuels.
So biofuels is derived from the living matter.
Biofuels are said to be carbon neutral. The amount of carbon dioxide released when they are burnt is the same amount of carbon dioxide used to make the fuel in the first place. However, some people argue that biofuels are using valuable land that could otherwise be used to provide food for the 800 million undernourished people around the world. So what are examples of biofuels? Simply burning wood counts as a biofuel. As we've been
Burning wood as counts as a
burning wood
biofuel.
for 600,000 years, there's not much I can say about it that you don't already know. So we're going to focus on a more complicated biofuel. Instead, biogas. Biogas. It's a surprisingly simple process to make biogas. Inside a sealed tank, bacteria and other microorganisms anaerobically digest different feedstocks in the absence of oxygen to produce biogas. This biogas can
So how biogas are produced? So inside a closed chamber, some bacteria are there. So that will anaerobically digest and they will produce biogas. Okay. This is a simple process of producing biogas.
then be used for energy. The tanks, known as digesters, are just like big stomachs, with lots of microorganisms inside to help with digestion. Like a stomach, the digesters need feeding. One of the clever things is that the food can be plant-based material, like energy crops, specially grown for generating energy, or farm waste materials like cattle slurry, or it can even be food waste, wastewater and sewage sludge. We can make a renewable energy from all these useless waste materials. How amazing is that? In go the feedstocks and the microorganisms digest away and do their magic. The temperature inside the tank is either about 35 degrees Celsius or it's hotter between 50 and 60 degrees. This depends on the type of
So this can be mesophilic bacteria where the temperature needs to be maintained at 35 degrees centigrade, and thermophilic bacteria where the high temperature is to be maintained. And at that temperature, the bacteria can function and they can digest and produce biogas.
microorganism inside the tank. Just like in your digestive system, the feedstock is stirred around inside the digester tanks to ensure the microorganisms are reaching the undigested material. The anaerobic digestion process takes somewhere between 14 and 40 days to complete, and results in biogas being produced, which is collected from the top of the digester tanks. Biogas is about 60% methane and 40%
So biogas is around 60% methane, 40% carbon dioxide.
with some other trace contaminants. The biogas can then be used to generate electricity, or even better, it can be cleaned up, compressed and injected into the gas grid as biomethane. Inside the tank,
So from the biogas we can use it as electricity and it can be differentiated to produce
we're
biomethane.
left with a waste product called digestate. Another fantastic thing about this process is that the waste digestate is a great fertilizer. It can be used instead of petrochemical fertilizers. So not only has renewable gas been produced,
So the digestate can be used as petrochemical fertilizers.
but an organic fertilizer is made. Bioethanol is another example of biofuel.
So biomethane was one kind of biogas, right? So bioethanol is another example of
Made
biofuel.
by allowing yeast to ferment sugar.
So it is produced by allowing yeast to ferment sugar, and that is how bioethanol is
The sugar
extracted.
source can come from sugarcane and also fuel crops like maize, wheat and some grasses. The ethanol product can be mixed with an alkaline fuel like petrol or diesel and used to fuel cars. These mixed fuels can be 85% bioethanol and only 15% fossil fuel. Whilst fossil fuels are
So they can use in the transportation, right? 85% can be
still being
bioethanol
burned,
and
significantly less
15% will be fossil fuel. Okay.
fossil fuels are burned overall. This process works best in countries where lots of the raw material, sugar, is grown, like Brazil. So there you have it. Biofuels are a useful alternative to fossil fuels. They're not a perfect alternative, but they certainly have some advantages.
If you liked the video, give
So here for this video, I want to acknowledge this Few School Global Education. So the video is very easy to understand. Next, okay, so now the examples of biomass. So biomass examples are only the kernels of corn, then the mats of algae, then stalks of sugarcane. So there are types of biomasses. There is woody biomass. Woody biomass includes coconut oil, palm oil, poplar, pine. Okay, so how woody biomass are produced? So generally burned to this solid raw materials are burned to heat space or heat water to produce steam to generate electricity via a turbine generator. And the non-woody biomass are this corn, sugarcane, soybeans, and algae. So these are the non-woody, and they are used. Used for production of biofuels. So woody biomass are used for production of electricity, and they are used for production of biofuels. So these are the examples of biomass. Next, biomass provides high density energy source. Is it true or false? Biomass provides high density energy source. and it is true, obviously. Next, what will be produced if pre-treated lignocellulose is going through pyrolysis? Oh my God. What will be produced if pre-treated lignocellulose is going through pyrolysis? The answer is bio-oil. So bio-oil and biogas, biodiesel all are different. Okay, so you have to remember the difference. So it might be confusing, but pre-treated lignocellulose is going through pyrolysis. It will produce bio-oil. Next, how is biodiesel produced? So there is waste oil, suppose. Waste oil will do esterification and can produce biodiesel. Also glycerol. So both can be produced, but mainly waste oil after esterification produces biodiesel. Also microalgae after oil extraction and then the esterification can produce biodiesel. Okay, so these are the two methods of production of biodiesel. Next, what percentage of cellulose is present in wood? What percentage of cellulose is present in woods? The answer is 40 to 50%. So 40 to 50% cellulose is present in wood. Next question is, name the contents of hemicellulose. So hemicellulose is a polysaccharide. Hemicellulose is a polysaccharide derived from several sugars, and it consists of glucose, xylose, mannose, galactose, rannose, and arabinose. So these are the contents of hemicellulose, and 20% of biomass plants have hemicellulose. Okay. Next, phenylpropane units are present in hemicellulose. Is it true or false? Phenylpropane units are present in hemicellulose. The answer is false because it presents in lignin. It presents in phenylpropane units are present in lignin. Next, name the different components of lignin. Name the different components of lignin. The first one, so A is the p-coumaryl alcohol. B is synapyl alcohol. And the C is coniferyl alcohol. So these are the different structures of the lignin component. So you can see there is only OH here. Here there is OCH3, OH, OCH3 are there. The last one only OCH3, OH are there. So these are the different structures of a lignin component. Next, what are the two processes of producing cellulosic ethanol? So to produce cellulosic ethanol, the lignin and hemicellulose must be separated from the cellulose. So the cellulose enzyme can hydrolyze the cellulose, creating glucose units. So there are two processes. The first one is the biochemical process. Biochemical process is ethanol created through a series of steps. Those are pre-treatment, enzymatic saccharification, and fermentation. Second one is the thermochemical process. Here, ethanol is created by gasification, syngas fermentation, or Fischer-Tropsch reforming. So these are the two processes, biochemical and thermochemical process, from which cellulosic ethanol can be produced. Next question, how to remove the recalcitrance of lignocellulose? So in the production of lignocellulosic based biofuels, pre-treatment is necessary to remove the recalcitrance of lignocellulose. This allows for enzymes and chemicals to have access to cellulose. So, but how these recalcitrants are done in pre-treatment? The first process is separating the lignin and hemicellulose. Second one is the pre-hydrolyze some of the cellulose. Third one is the destroy crystalline structure of cellulose. And the fourth one is the reducing the size of the feedstock. So these are some of the steps in pre-treatment we need to do to remove the recalcitrance of lignocellulose. Next question, discuss the corn-based and lignocellulosic-based biofuel flowcharts. So in the flow chart we will see just a minute, yeah. So in the corn-based biofuels, you can see first the corn grills are grinded, they will produce corn grits. Then the liquefaction is happening where enzymes are passed that will produce corn slurry. Corn slurry will go to the saccharification section. Here again enzymes are used, enzymes are sent and steam is sent. Then it sent to the fermentation section. And in the fermentation section, the yeast is given. So yeast is pre-incubated in the incubation tank where oxygen and urea are supplied. From there, yeast is collected and yeast is given to the fermentation cells where it produces carbon dioxide. And first it produces beer, that is less than 20% of ethanol. It will lead to, now the purification is needed, right? So it will lead to stripping. So from stripping, solid and liquid part will be separated. So solid part will go to the centrifugation and then evaporation. So soluble proteins are evaporated. Then the dry distillate grains, the wet distillate grains, that is 50% moistures, are collected from the bottom part of the centrifugation and it is dried and produces dry DDG, that is dry distillate grains. That is only the 10% moisture, and that will be sold to the market. And in the stripping section, the liquid part, there are 60 to 70% ethanol, and that will lead to rectification. That will go for azeotropic ethanol, and azeotropic ethanol will pass through the molecular sieve, and that will produce anhydrous ethanol. So this is the production of corn-based biofuels. Next comes the lignocellulosic-based biofuels. So lignocellulosic-based biofuels, there are three components: lignin, cellulose, and hemicellulose. So they need to be treated separately. So here comes the gasification process. So in the gasification process, what happens? Pre-treatment happens, then the direct gasification happens at temperature 853 degrees centigrade and 21 bar. Okay. Then the steam reforming happens at 21 bar. So in the gasification section, it will produce the steam gas, right? Then it will pass through the filter. In the filter, also the temperature is 500 degrees centigrade. Then it goes to the HBC removal. HBC removal also separated the steam gas, and it will go to the bypass or PSA H2 section. So from there it will go to the PSA CO2 removal section, it will go to the MEA section, then it will go to the catalytic section, the steam gas at 300 degrees centigrade, and it will go to the directly distillation section, and some of the part will recycle back to the HBC removal, and finally from the direct distillation section ethanol is produced. This is the thermochemical ethanol production from biomass. Next is the hydrolysis. So this is a thermochemical where gasification is used. Next is the hydrolysis. So here pre-treatment dilute acid treatment happens in both ways, solids handling and liquid utilization happens, and then it goes to the hydrolysis section. Then next comes the fermentation, next the solid separation, and from the solid separation lignin is separated and the rest of the products go into the beer column. Then the molecular shift and the fuel ethanol is achieved. This is the hydrolysis with ethanol production from switchgrass. Here in the previous case the raw material was biomass, here it is switchgrass. Then so these are the two methods in the lignocellulosic case. So when you have asked for the flow chart, so you have to write the flow chart for both the cases. And for lignocellulosic, there are two methods, that is one is hydrolysis based and one is gasification based. Next question and the last one is what are the techniques of cultivating algae? So there are two steps of cultivating algae. So there are diverse ways as well, but here two steps are mentioned. One is the open ponds. So in open ponds, algae is grown in a pond in the open air, right? A simple design and low capital cost because there are multiple open ponds around us. You can see less efficient than the other scene, but other organisms can contaminate the pond and potentially damage or kill the algae. So, but this is the advantage of the open ponds. Disadvantage of the open ponds. Second one is the closed loop systems. Okay, here similar to open pond but not exposed to the atmosphere and use of a sterile source of carbon dioxide could potentially be directly connected to carbon dioxide sources and thus use the gas before it is released into the atmosphere. So the closed loop system, what carbon dioxide produce? It is not released in the atmosphere, which will ultimately reduce the pollution. And there are photobioreactor also complex, expensive closed systems. So the third method is the photobioreactors. This is the complex, expensive and closed system, significantly higher yield and better control. So these are the three methods for cultivating algae. So that is from my side. I hope you find this in today's session there are mostly the subjective questions because we need to know in detail all the processes and it's how the process works, the flow charts and all, what the raw materials, what are the products. So there is also maybe some confusion because there is biogas, bioethanol, biodiesel. So these are the same things almost, but production process is different. So you need to go through the slides very carefully. And if you have any question, you can write back. Until then, goodbye.